Welcome to Lesson 4.5, Linear Approximations. This lesson covers Topic 4.6 from the 2019 course and exam description for AP Calculus AB, Approximating Values of a Function Using Local Linearity and Linearization. This lesson will cover standards CHA 3.f.1. The tangent line is the graph of a locally linear approximation of the function near the point of tangency. CHA 3.f.2. For a tangent line approximation, the function's behavior near the point of tangency may determine whether a tangent line value is an underestimate or an overestimate of the corresponding function value. Our instructional objective is that students will be able to use the equation of a tangent line in order to approximate a value on a curve. And our inquiry question is, how can we use derivatives to solve real-world problems involving rates of change? Now let's take a broad look at linear approximations. In this lesson, we're going to approximate values of a function using local linearity and linearization. In Unit 2, we briefly looked at the idea of local linearity when x equals a. Zooming in on a function, we discovered as we zoom in on a function y equals f of x, the straight line that appears at a given point has a slope equal to the derivative f prime of a. And the equation for the tangent line at the given point was defined as y equals f of a plus f prime of a times x minus a. And so this means that f of x is approximately the linear equation, f of a plus f prime of a times x minus a, so long as x is in the neighborhood of a or is close to a. In this lesson, we'll expand our investigation for a deeper understanding. Linear functions are much easier to work with than higher degree polynomials, functions with radicals or rational exponents, and certainly transcendental functions. And so if we have the derivative at a particular point, we have a slope, and if we have the point, it's very easy for us to derive a tangent line. And now for any value of a that is in the neighborhood of our x value, we can use our linear equation in terms of the slope f prime of a to find an approximation for x. So you're going to need to commit to memory this linear function for the tangent line, and we'll do a few examples where we use this function to produce an approximation. And then we'll talk about whether or not our approximation is an overestimate or an underestimate. So one more time, suppose f is a differentiable function at a point x equals a, then for values of x that are near a, our tangent line approximation, f of x, that's a y value, is given by y equals f of x, is equal to f of a, that's the y value corresponding to x equals a, plus f prime of a times quantity x minus a. We define the expression f of a plus f prime of a times x minus a as the local linearization of f near x equals a. So when you see that term, local linearization, what we're talking about is the tangent line at point A. If we consider that point a, f of a, that's an xy value, to be fixed, then f of a and f prime of a are constant values. And so we have a constant linear function if x is close to a. Now let's talk about the error or deviation for a linear approximation. When we talk about the error, we're not talking about a mistake. We're just simply talking about the difference between the actual value and the predicted value. So the error, which we'll call e of x, in the linear approximation is simply the vertical gap between the actual curve and the tangent line. In a moment, we'll take a look at a picture in example 1 that will illustrate this. The error can be calculated by finding the exact value minus the approximation, and then taking the absolute value. So in symbolic form, e of x is equal to delta f, the actual change in our y values, minus f prime of a times x minus a. Percentage error is the error, the absolute value of the exact minus approximation divided by the exact value times 100%. This is the same as the percent change formula that you may have seen earlier in algebra. Example 1 says that it can be shown the best linear approximation to f near a is the tangent line approximation. Label the true value of f of x, the tangent line, and the approximation. Okay, you know what? Let's begin by labeling the tangent line. So the tangent line is the line that is tangent to the curve at the point x equals a, and so that's going to be this line right here. So this is our tangent line. Now the exact value is the value on the curve corresponding to our value of x. And so this is going to be our exact value, or our true value, and we're just simply going to call that f of x. So that's the y value, the y value on the function corresponding to the x value. Now the approximation is actually this point right here. So we can label this our linear approximation value. And you'll notice that the y value here comes from taking our f of a value, this initial y value, and adding to it this difference right here. Well, what is that difference? Well, that difference is going to be the unit rate of change times the distance that we travel on the x-axis. Well, the unit rate of change is going to be the slope, which is f prime of a, times our delta x, which is x minus a. And so this is the y value, f prime of a times x minus a. This is f of x, and so we can see our error is actually going to be the difference, the vertical difference between those two y values. And so that's going to be f of x minus f prime of a times x minus a. And we are just interested in the absolute value. And so that's what our error is going to be. Okay, so let's look at a procedure for finding a linear approximation for f of x. So when you need to write a linear approximation for f of x centered at a given value, say x equals c, and you need to approximate at a value in the neighborhood of x equals a, let's call this new value x equals a and proceed as follows. First, write the point slope equation for the tangent line at the point c, comma f of c. Then isolate y. Rename this equation as L of x. Substitute your value for x equals a in the equation, L of x, and be sure to write the notation correctly. We need to write that f of x is approximately L of x, but L of x is equal to f of a plus f prime of a times quantity x minus a. In step 4, if we need to explain whether or not L of a is an overestimate or an underestimate, consider the behavior of the function in your local neighborhood. If the function is concave up at x equals c, L of a is an underestimation. If the function is concave down at x equals c, L of a is an overestimation. Step 5, when finding the error or accuracy of an approximation, we'll do this using our calculator. Find the absolute value of the difference between the exact amount and your approximation. Then the error should be stated as being less than 10 to the negative p, where p is the number of zeros in your result. So for example, the absolute value of our error would be less than 10 to the negative third if our result was 0.000147. And then finally, in step 6, if you need to find the percentage error, then we will take our error and divide that by the exact value, take the absolute value, and multiply by 100. Now let's look at example 2. The function f is twice differentiable, where f of 3 is equal to negative 2, f prime of 3 is equal to 5, and f double prime of 3 is equal to 1. Write the equation of the tangent line, then use the equation to find the value of f of 3.1. Well, let's think about it. I am going to need this information here. F of 3 equals negative 2. This tells me that I have the point 3 comma negative 2. I need f prime of 3 because this gives me the slope of the tangent line that passes through the point 3 comma negative 2. I don't need the second derivative. That's just extra information. So let's start by writing f of x is approximately L of x, which is equal to f prime of 3 times x minus 3 plus f of 3. And so that means that f of 3.1 is approximately L of 3.1, which is equal to, and f prime of 3 is 5 times 3.1 minus 3 plus, and f of 3 is negative 2. So this gives us 5 times 0.1 minus 2 equals negative 1.5. So this will be our solution. Linear approximations will do a great job of estimating values for x equals a, provided you stay in the small neighborhood near f of x. The farther away from x equals a we move, the worse the approximation becomes. While there is no easy method to determine how near or far away we can move from our point of tangency, we can predict the amount of error to give us an idea of how good the approximation models the actual value. Let's look at a famous linear approximation that is used to describe vibrations, pendulum motion, and is used as a method to simplify formulas in optics.
Let's take a look at example 3. We are told to consider y equals sine x at x equals pi over 3. In this problem, they have given us the ordered pair corresponding to the angle pi over 3, but don't assume that you'll be given this on the AP exam. You need to be able to derive the unit circle from memory in order to find exact values such as these. Also, remember that on the unit circle, the ordered pairs are of the form cosine theta, comma sine theta. So that means that sine pi over 3 is equal to square root of 3 over 2, and cosine pi over 3 is equal to 1/2. In part A, they give us an approximation of pi over 3 in radians and to 8 decimal places, and then ask us to find the linear approximation for x equals 1.05. Well, 1.05 is in the neighborhood of 1.0471975, so it is appropriate for us to approximate with local linearity. First, let's begin by writing our approximation. This will tell us what we need to find. Note that we are finding the tangent line for the x value of pi over 3, so this is the value for a that we will be substituting. F of x is approximately equal to L of x, which is equal to f prime of pi over 3 times quantity x minus pi over 3 plus f of pi over 3. Okay, we need to find f prime of pi over 3 and f of pi over 3. Let's start with the function that we were given. F of x equals sine x, so f of pi over 3 is equal to sine pi over 3. And from our ordered pair on the unit circle, we have that sine pi over 3 is equal to radical 3 over 2. Next, we find the derivative of sine. F prime of x is equal to cosine x, and f prime of pi over 3 is equal to cosine pi over 3, which is equal to 1/2, again from the unit circle. Now we can write the tangent line equation. L of x is equal to 1/2 times quantity x minus pi over 3 plus square root of 3 over 2. Next, we enter this equation into our graphing calculator. To store our equation, press y equals. We then enter 1 divided by 2 times, open parentheses, x minus second function, pi divided by 3, close parentheses, plus second function square root 3, right arrow, divided by 2, enter. This puts our equation into the memory location y1, where we can substitute any value. Press second quit to exit the equation editor and return to the main screen. Your calculator may not have shortcuts, so I will avoid using them. The keystrokes to get y1 are vars, yvars, function, y1. Then open parentheses and 1.05, close parentheses, enter. So we can write f of 1.05 is approximately L of 1.05 is approximately 0.867426, although you only have to report to 3 decimal places. Next, let's find the error of your approximation in Part B. In Part B, we are asked to find the error of the approximation. To do this, we need to take the value of f of pi over 3 minus L of 1.05. This is approximately the absolute value of sine pi over 3, 0.86426. On the TI, press y equals to enter the equation editor, then enter sine x. Now we have both our original function and approximation. Press second quit main screen. Now we will find these values. Vars, y2, open parenthesis, second pi divided close parenthesis, minus vars, yvars, function y1, open parenthesis, 1.05, close parenthesis, enter. This gives us a value of negative 0.014. So taking the absolute value of this output, we have that the absolute value of sine pi over 3 minus 0.867426 is approximately 0.014. And since there are 2 zeros between the decimal and our first non-zero number, that means that the value of our error is less than 10.
In example 4, we are asked to find a linear approximation to y equals 2 to the x at x equals 3. Then we are asked to use the tangent line to find an estimate for x equals 2.97. First, we will write our linear approximation. F of x is approximately L of x is equal to f prime of 3 times quantity x minus 3 plus f of 3. F of x is 2 to the x, so f of 3 is 2 to the third power, which is equal to 8. Next, we need f prime of 3, so we will take the derivative of 2 to the x. F prime of x is natural log of 2 times 2 to the x. Thus, f prime of 3 is natural log of 2 times 8, or 8 ln of 2. Next, we substitute into our linear function, so L of x equals 8 natural log of 2 times quantity x minus 3 plus 8. Let's input this function into the TI. Press y equals, and then for y1 enter 8 times ln2 close parenthesis times open parenthesis x minus 3 close parenthesis plus 8. Now that we have stored L of x, we need to substitute the value 2.97 to find our approximation. Press second quit, and then vars, yvars, function y1, open parenthesis 2.97, close parenthesis, enter. This gives us our approximation 7.83364. So f of 2.97 is approximately L of 2.97 is approximately 7.83364. In example 5, we are asked to approximate 2.01 to the 5th power. Use your calculator to find the accuracy of the approximation. Is the linearization an overestimate or underestimate? Explain. Well, f of x equals x to the 5th And at x equals 2, we have f of 2 equals 2 to the 5th, or 32. Taking the derivative, we apply the power rule. And we have f prime of x equals 5x to the 4th. So f prime of 2 is equal to 80. Now we can write L of x equals 80 times quantity x minus 2 plus 32. Let's put this function into the TI. Press y equals. Now for y1, enter 80 times open parenthesis x minus 2 close parenthesis plus 32. To return to the main screen, we press second quit. And now to find our approximation. Vars, y vars, function, y1, open parenthesis, 2.01, close parenthesis, enter, and we get 32.8.
Now we will enter our original function for y2 so that we can calculate the error. Y equals down arrow to y2, x to the 5th, enter.
Now second quit, vars, y vars, function, y2, open parenthesis, 2.01, close parenthesis, minus vars, y vars, function, y1, open parenthesis, 2.01, close parenthesis, enter. So the absolute value of our error is 0.008. This means the absolute value of the error is less than 10 to the negative 2. Now we can graph both functions to determine if this is an over or an underestimate. So press Window, Enter. Let x min be negative 1 and x max be 3 with an x scale of 1. Then y min is negative 1 and y max is 10 with a y scale of 1. Press graph and we see that the power function is concave up with the linear equation below. Thus, our tangent line is giving an underestimate. Finally, for our response, we state that the graph is concave up and 32.8 is an underestimate of the actual value.
Let's take a look at example 6. Find the linear approximation of g of x equals the cube root of x at the value x equals 8. Use the linear approximation to approximate the value of cube root of 10 and cube root of 16. Compare the approximate values to the exact values, and then finally, find the error of your approximations. So let's start by writing out what we're going to do. So g of x is going to be approximately L of x, which is equal to g prime of a times x minus a plus g of a, where in this case a is equal to 8. So of course g of x is the cube root of x, which is the same as x to the 1/3 power. And I write it like that so that I can differentiate this easily using the power rule. It becomes 1/3 power times base down 1, x to the negative 2/3, and that's going to be equal to 1/3 times the cube root of x quantity squared. Now, g of 8 is the cube root of 8, which is 2. G prime of 8 is 1/3 times the cube root of 8, which is 2, squared, which is 4, or 1/12. So now we can just write down L of x, 1/12 times x minus 8 plus 2. And this is the function that you'll enter in for y1 in your graphing calculator. And let's go ahead and see if we can find L10. And so substituting in, that's going to be approximately 2.1666 7, and then L of 16 will be approximately 2.66667. And let's see what the cube root of 10 is. So for this we get 2.15443, and the cube root of 16 gives us 2.51984. So our first error is going to be the absolute value of L10 minus G10. So this gives us an error of 0.012 to 3 decimal places. And that's going to be less than 10 to the negative 1. And let's do this again for x equals 16. So L of 16 minus G of 16, 0.147, which is less than 1. In example 7, we're told, let f be a function that is differentiable for all real numbers. The table below gives the values of f of x and its derivative f prime of x for selected values in the interval from negative 1.0 to 1.0. The function is concave up in this closed interval. In part A, write an equation of the line tangent to the graph of f of x where x equals negative 0.7. So we'll begin by writing our approximation. F of x is approximately L of x, which is equal to f prime of negative 0.6 times x minus negative 0.6, so that's x plus 0.6, plus f of negative 0.6. So L of x is equal to f prime of negative 0.6. So we find negative 0.6, and f prime of x is negative 2. So we have negative 2 times x plus 0.6 plus, now f of negative 0.6. f of negative 0.6 is negative 51. So negative 51. Negative 2 times x plus 0.6 minus 51. In part B, we're asked to use this line to approximate the value of f of negative 0.5. So f of negative 0.5 is going to be approximately L of negative 0.5, which would be equal to negative 2 times negative 0.5 plus 0.6 minus 51, and so this is going to be equal to negative 0.2 minus 51, which is equal to negative 51.2. So f negative 0.5 is approximately negative 51.2. And then in part C, is this approximation greater or less than the actual value of f of negative 0.5, and give a reason. So remember that in the original problem they told us that the function is concave up. So we're going to write, since f of x is known to be concave up on the interval negative 1 is less than or equal to x is less than or equal to 1. The tangent line lies below curve, and the approximation would be less than the actual value of f of negative 0.5. And if we wanted to draw a picture to go along with this, we might have some sort of concave up curve and tangent line. So here we have our point of tangency, negative 0.6 comma negative 51, and then we have this point on our line that is negative 0.5 comma negative 51.2, and this vertical distance here is the deviation from the original function given by our tangent line, the error. In example 8, we're told to write the linear approximation equation for f of x equals 1 over x minus 1, at x equals -1. In part A, find an approximation for f of -1.2. Let's begin by taking the derivative of our function f of x. So 1 over x minus 1 is equal to x minus 1 to the -1, so that f prime of x is equal to, via the power rule, -1 times x minus 1 to the -2, and the derivative of x is just 1. First, let's look at our approximation. F of x is approximately L of x is equal to f prime of -1 times x minus a -1 is +1 plus f of -1. So let's see what f of -1 is. F of -1 is going to be 1 over -1 minus 1, and that gives us -1/2. F prime of -1 gives us -1 minus 1 is -2, quantity squared is 4, -1/4. So we have f of x is approximately L of x equals -1/4 x plus 1 minus 1/2. So now let's do f of -1.2. So that's approximately L of -1.2, and that's equal to -0.25 times -1.2 plus 1 minus 0.5. So L of -1.2 is going to be equal to -0.45. In part B, they want us to calculate the error of the approximation. So remember that the error is equal to the absolute value of the exact value minus the approximate value. So this would be -0.454545, so on and so forth, minus -0.45, which is equal to 0.0045. So this means that the error, the absolute value of the error, is less than 10 to the, and we have 2 zeros, so we'll put -2. In example 9, we're told, given the implicit curve x squared plus natural log x divided by y equals 1, write the linear approximation of the tangent line at x equals 1. Now we're given the graph here of this function, but if you wanted to do this on your graphing calculator and you didn't have a graph to work with, you could graph this, but you would have to put this in explicit form. I'll take a minute and talk about that. So we start with our function x squared plus natural log, and you'll notice that I have x divided by y. Well, the quotient rule for logarithm says that the log of m over n is equal to the log of m minus the log of n. So via this quotient rule, we can write natural log of x minus natural log of y is equal to 1. Now, I need to get the natural log of y by itself. And so this gives us x squared plus natural log of x minus 1 equals natural log of y. And to get rid of the natural log, I need to raise both sides as the power of e, the base of the natural logarithm. And so this gives us y equals e to the x squared plus natural log of x minus 1. So this gives you a function that you can put into your calculator for y1 and then graph. But let's take this version of the equation here and use that as our starting point to find a derivative. So x squared plus natural log of x minus natural log of y equals 1. So we're going to use implicit differentiation, and this gives us 2x dx is just 1 plus, and the derivative of natural log x is just 1 over x minus, and the derivative of natural log y is 1 over y, but don't forget, we have to multiply by dy dx, equals, and the derivative of 1 is 0. I want to solve this for dy dx. So we get 1 over y dy dx is equal to 2x plus 1 over x. Dy dx is equal to 2xy plus y over x. Now, we want to know about the tangent line at x equals 1. So let's evaluate this slope dy dx at x equals 1. And so we are told that when x is equal to 1, y is equal to 1 because that ordered pair 1, 1 is on my function. So this gives us 2 times 1 plus 1 over 1 is equal to 3. So f of x is approximately L of x equals 3 times x minus 1 plus, and the y value, f of 1, is 1. And so this will be our tangent line. In part B, they say using the tangent line to the curve at x equals 1, find the number k such that the point 1.25k is on the curve. Okay, so let's rewrite our approximation. F of x is approximately L of x is equal to 3 times x minus 1 plus 1. So we can substitute directly from this point. 1.25 is an x value, k is a y value. And so we'll let k be equal to 3 times 1.25 minus 1 plus 1. This ends up being 1.75. Now in part C, they want us to calculate the error of the approximation. So the absolute value of our error is equal to the absolute value of f of 1.25 minus L of 1.25. Now let's find out what f of 1.25 is. So f of 1.25 is going to be equal to, and here's another good use for this formula we derived. This is what I can plug into to find out what f of 1.25 is. We just plug in 1.25 for x. So this is e to the 1.25 squared plus the natural log of 1.25 minus 1. And from our calculator we get 2.1938183. So 2.1938183 minus, and L of 1.25 is 1.75, gives us approximately 1.005 to 3 decimal places, which means that the error is less than 10 to the 20, so -2. Now let's also go ahead and find the percent error. That's going to be equal to f of 1.25 minus L of 1.25 divided by f of 1.25. And again, we'll take the absolute value. And then finally, we take that decimal and multiply by 100%. And this gives us 20.230%.